So today we're going to be looking at two things. One, the median of a triangle, and two, a proof related to the median of a triangle. So straight away, the median of a triangle is a line segment that we draw from any vertex to the opposite side, which dissects the opposite side, i.e. splits it into two equal lengths. As we can see here, all three medians have been drawn, FC, AD, BE, and you can see that they all meet in one point called G. So we call that the center of gravity, or we'll be using the term centroid. Super. Okay. What we're going to look to prove today then is, if we have a look at those medians, we're going to try and show then that this length here, AG, is 2/3 of the whole length of that median. Or another way of looking at it is that this length here has a 2-to-1 ratio with the shorter length here. Okay? And that applies to all medians. The longer side, you'll notice, is the one that comes from the vertex here, and the shorter side is the one, the other side of the centroid, which then goes on to intersect with the opposite side. So that's what we're going to seek to prove today. Let's rub all of that rubbish out. Before we can do that though, we need to look at the areas of these triangles. So let's rub this out. Bye. Now let's have a look then at triangle BGC. And it's split off, well, you can see that the base of that triangle is split in two. If you think about it, if you look at the height of each of these now separate triangles, here's our height, you'll see that triangle BGD and triangle DGC, both of those have actually got the same base and the same height. Now we know that the area of your triangle is half base times height, so if they've got the same base and height, that means that they've both got the same area. Now, we can use the same exact reasoning then if we go along. So if we now look at the two triangles enclosed here, AGF and FGB, again we can see now the height of this triangle, let's say it's over here, here's our height. We can see that both triangles, AFG and BFG, have got the same base and also the same height. So we can actually say that they've got the same area, which we're going to call Y. And if you follow that around and do the same again, you can actually see, again, here's the height of this triangle and also the two smaller triangles. We can actually say that triangle AEG and GEC have also got the same area. So let's call that W. Now, what can we do with that then? It seems that there's some kind of relationship between these areas. Well, if we look at the median FC, we can see that FC actually divides the triangle in half. So that means that Y plus W must be equal to Y plus X. Now, it doesn't take a genius to work out then that means that 2W must equal 2X, W must equal X. Okay, so that's good. If we'd have chosen another median, we could have had a look at another relationship. Let's just delete that one. We can then write in that, well, okay, Y plus X must be equal to W plus X. And again, we can clearly see then that Y now is equal to W. So if this is the case, then this must mean that Y is equal to W is equal to X. All of these areas are in fact equal. Okay? So we could say that each of these areas, let's call it X. So how are we going to use this then to prove our relationships over here? Well, we're going to use very similar idea about the heights of triangles and the bases to try and prove these relationships, like we showed in the first thing over here with the areas. Okay, if we look then at, let's concentrate on triangle ABE. Okay, we can see that the area of triangle ABE is 3x. Okay, now if we split this up then, here we go into two triangles. We've now got two triangles with different bases, but again the same height. So if we try and find the relationship between their areas and their bases, we might find a relationship that we're looking for. Let's call the base of the bigger triangle base 1, and let's call the base of the second triangle, GE, let's call that base 2. So we can see then, if we write down the relationship between their areas, let's say the area of AGB, which is going to be half base 1 times height, that must be equal to 2x. And then if we say, okay, well, let's find the ratio then of these sides, of these areas. The area of the second triangle is going to be half base 2 times height, and we know that that's going to be equal to x. Okay, that must mean then that if we cancel all of these out, base 1 over base 2 is equal to 2, or they've got a ratio of 2 to 1. Okay, and that's exactly what we were looking for. If you have a look here, concentrating on BE and have a look here, we can see that BE must be 2/3 of BG because they have a 2 to 1 ratio. Again, you could go through, so to prove the other three relationships, all we'd have to do is go around and just choose different triangles along different medians. So again, in this one, we could split this into two triangles here, and you can see that ACG has got the same height as GDC, but it's got double the area. So obviously it must have double the base, and again giving us a 2 to 1 ratio between the longest part of the median and the shorter part of the median. Okay, that should be sufficient to show that they're proved though.